Thank you very much for the introduction and also for the invitation. I think it would be much nicer if we could all meet in person in Gdańsk, but let's make the best of the present situation. So I will try to share my screen. I hope this works. So I would like to take this opportunity to talk about a joint work with Andreas Blum and Ion Nekita about incompatibility in GPTs. So to tell something about motivation, why to study incompatibility. So the existence of incompatible measurements is one of the fundamental non-classical features of quantum mechanics. It was observed already in the early days, but it still cannot be said that it is fully understood. Today, it is recognized as a valuable resource in quantum information theory, since it is a crucial ingredient in many protocols. It is well known that to violate any Bell inequality, incompatible measurements are necessary. So therefore, it is an important task to characterize, detect, and quantify incompatibility in some ways. And we will do it in the setting of general probabilistic theories, which is an operational framework for description of physical theories, containing both classical and quantum theory, but also some like toy models used in quantum foundations or in the study of some specific non-classical phenomena. And incompatibility can be naturally defined also in this broader context, and in fact incompatible measurement exists in any non-classical GPT, so it makes sense to study it there and perhaps compare the incompatibility to that one in the quantum theory. And also we can use some convenient tools like convexity, ordered vector spaces, or tensor cones, at least in the setting of GPTs we are using. And from this broader perspective, we show that we can relieve a relation of incompatibility to other problems in other areas in mathematics, which allows us to find some results like bounds on incompatibility degree. But I think the existence of these relations is what is most interesting. So let me start. We will work with tuples of measurements with finitely many outcomes. So each of these measurements can have a different number of outcomes, and we collect all the outcome numbers in this K, which describe the shape of the measurements we are working with. And from the most general point of view, a measurement can be seen as a sort of box with a button and some lights with labels. And we have a G tuple of such boxes. We can choose one of them, push the button, and then a light will flash, indicating the outcome of the measurement. And we say that these measurements are compatible if they all can be obtained from a single joint measurement, which can have many more outcomes, and all the measurements in the tuple can be obtained by some post-processings. This is also called joint measurability. So if the measurements are performed on the quantum systems, then they are represented by a POVM. So I think you all know, but just let me tell you quickly. So it is a collection of operators between 0 and 1s, also called effects, which sum up to the identity. And these POVMs are related to outcome probabilities through the Born rule. So for any state, the probability of the outcome I is given by this trace. And in the special case of binary measurements or with two outcomes, can be represented just by the effects. Now the question is how to characterize compatible POVMs or compatible effects. So in some particular cases, this is easy, but in general, it's more complicated. So let us first look at the most simple possible case here for pairs of qubit effects. So using the block representation, qubit effects are of this form. Here, sigma is the triple of Pauli matrices, sigma x, sigma y, and sigma z. A is a vector in a three-dimensional Euclidean space, and alpha is some real number, and this operator is an effect if and only if this inequality is satisfied. And for pairs of such effects, it is known already, was proved already a long time ago by Bush, that there is a necessary condition for compatibility, which is this inequality for these norms. And in the case that A and B are unbiased effects, which means that both alpha and beta are equal to 1, then also the converse holds. So this is a necessary and sufficient condition for compatibility. And an observation which will be important in the first part of the talk is that this quantity here is a tensor norm. So let me quickly remind you what this means. So we have two Banach spaces, X and Y, and we will always work with finite dimensional spaces. And a cross norm is a norm on the tensor product, which is multiplicative on simple tensors. And also the dual norm is multiplicative on simple tensors on the tensor product of the dual spaces. There are two distinguished cross norms. First is the injective norm and the projective norm. These cross norms are dual to each other, and also they have the property that any other cross norm is between these two, and this is actually the condition that characterizes all cross norms. So now to return to cubic effects, we take the two vectors in L2, 3, and taking the basis elements in R2, we form this tensor, and it will be convenient to endow this two-dimensional space with the L infinity norm. Then we can compute the two cross norms. So the injective cross norm is just this maximum of the norms, and the projective cross norm is the value we had before. So from this we can conclude that if we have two operators of this form, then first A and B are effects which are necessarily unbiased, if and only if the injective cross norm is less or equal to 1. And moreover, A, B, and are compatible effects if and only if the projective cross norm is less or equal to 1. Now the purpose of this talk is to show that this is no coincidence, that actually compatibility of effects is characterized by tensor cross norms for any finite number of any effects in any GPT, and it will be also shown that for some particular types of GPTs, we can have exactly the same result as we had for qubits, but with arbitrary number of effects. The next point is that the cross norm is a compatibility degree, which is very well known and naturally defined. And we can bound this compatibility degree of G effects by the projective injective ratio. So this is like this expression. This ratio was studied also by Guillaume Aubrin and his collaborators in a different context. But they obtained a number of properties of this ratio in many situations, and we can make use of their results. And for measurements with more outcomes, this will not work so nicely, but we will have to find other ways to characterize incompatibility. And as I mentioned, we will work in the setting on general probabilistic theories. So let me introduce some basics first. So we chose the setting of GPTs, which is excellently described in a PhD thesis by Ludovico Lamy. So there, the GPT is a triple, where this here is an ordered vector space with finite dimensions. So a real vector space with a positive cone, which defines an ordering in the space. And this is a unit effect, which is a strictly positive functional on the ordered vector space. And this unit effect defines a special distinguished base of the positive cone, of positive elements such that it is equal to 1. And this is the set of states. This space is endowed with the base norm. This is a well-known definition of the base norm. The dual ordered vector space will be usually denoted by A and A plus. So A is a dual vector space and A plus is a dual cone consisting of positive functionals over V. And it's easily observed that the unit effect is an interior element in the dual cone. It means that it's an order unit in A, and it defines an order unit norm in A. We will always see A and V as endowed with their respective base norm or order unit norm. So for some examples, there are classical systems where the vector space is just Rd, and both the cones are the simplicial cone. So here the cone is self-dual. This is a cone of elements with some non-negative coordinates, and the unit effect is just the vector of ones. Here the classical state space is a probability simplex of delta D of probabilities over the elements. And the norms, the base norm is equal to the L1 norm, and the order unit norm becomes the L infinity norm in Rd. Another important example is that of quantum systems. Here the spaces are formed by self-adjoint complex and bind matrices, and the cones are again self-dual, the cones of positive semi-definite matrices, and the unit effect is given by the identity matrix. And here the quantum state space, of course, is the set of density matrices or positive matrices of trace 1. And the base norm becomes the trace norm, and the order unit norm is the usual operator norm in matrices. There are also some other interesting examples which will be mentioned a bit later. The elements in the positive cone, so between 0 and 1, are called effects, and these are functionals which maps states to probabilities. Values between 0 and 1, and therefore can be interpreted as binary measurements in a very similar way as quantum effects through the Born rule. More generally, measurements with more outcomes are given by tuples of effects summing up to the unit effect, and again we have a Born rule like this. And any such measurement can be interpreted as an affine map that maps states to probability simplex delta K. And now we can define compatibility of measurements in this context. So let us have a G tuple of measurements with these outcomes. We said that the measurements are compatible if they all can be obtained as marginals of joint measurements, where the outcome set is the product of all outcome sets of all measurements. And the fact that these measurements are marginals means that all the measurement effects can be obtained by summing over appropriately over the effect of the joint measurement. And it was proved by Martin Plavala, a very nice result, that all measurements are compatible if and only if the GPT is classical, so it means that the state space is a simplex. To define a compatibility degree, the usual way to do is to mix the measurements with some noise and see if this becomes compatible. So for this we choose trivial measurements. So it's just measurements such that all effects are multiples of identity, and this means that the outcome is just chosen uniformly over the set of outcomes. And for the tuple of measurements and some coefficient s between 0 and 1, we form these convex mixtures with the trivial measurement. And the compatibility degree is defined as the largest coefficient such that these mixtures are compatible. So this can be easily seen here. So notice that these trivial measurements are always compatible with everything. And if f is incompatible, then at some point we just cross this line here. And this would be the compatibility degree. We can also define the smallest compatibility degree which can be attained on the given GPT by measurements with the given sets of outcomes. This is some property of the GPT in question. So having introduced the basic playground, let's look at the compatible effects in GPT. So here I will concentrate on effects, so two outcome measurements. So let us first take a G tuple of elements in A and form this tensor, similarly as we did for the qubits. So here, instead of the effects themselves, it is convenient to use these sort of shifted elements. And these will be seen as elements in the tensor product. Here we take the L infinity norm, and A is endowed with the order unit norm. Yes. Sorry. Okay, can you hear me? Can I continue?
Yes, please continue.
Okay, thank you. So let us look at the interpretation of the two norms, the injective and the projective cross norms in this tensor product. So to compute the injective cross norm is again easy. It's just the maximum of all these norms. And clearly, this is less or equal to 1 if and only if these elements are really effects. So what about the projective cross norm? So this here is the expression for the cross norm, but it seems that in general, there is no way how to connect this cross norm to compatibility. So what we have to do is take another norm with this C norm, which has a similar expression, but is slightly different. And it turns out that this is again a cross norm. In particular, it lies between the injective and the projective norm. And what is interesting about this cross norm is that this characterizes compatibility. So the F1 to Fg are compatible effects if and only if the norm of the corresponding tensor is less or equal to 1. And another nice property is that this norm can be computed by a conic program. Using this characterization, we can relate this norm to compatibility degree in a very easy way. It turns out that this is just the norm of the corresponding tensor to the -1. And the smallest attainable compatibility degree is related to the ratio of the C norm and the injective norm, which can be lower bounded by this projective injective ratio to the -1. So from these relations, we can find some bounds on this quantity. So this comes from the work by Obran and collaborators. And here, this first bound, so for G-1 is actually well known. It is rather easy to find a joint measurement for convex mixtures with this coefficient, but this dimension-dependent bound seems to be new. We also have a common lower bound for all G. This pi1 is something which is called the one summing constant. So here is the definition. But these one summing constants or p summing constants are well studied in the theory of Banach spaces, and these constants are actually computed in many cases. So again, we can use some information on this. So there is a special kind of GPTs called centrally symmetric, which means that the state space is isomorphic to the unit ball of some norm in RD. So in this case, the space V is just this product, and the positive cone can be expressed as these pairs. So lambda is a positive number, and the norm of x is less or equal to lambda. And the unit effect is just this pair, 1 and 0. And dual space has a very similar characterization using the dual norm. So again, these are some tuples such that this happens. An important example, of course, is the set of qubits where the state space is isomorphic to the block ball. Now, what happens to the tensor norm in the centrally symmetric GPTs? So if we take any element in this tensor product, then it has this decomposition to this pair. So there's some element in the infinity space and some vector tensor phi prime in the tensor product here. And the injective norm can be related to the injective norm of this phi prime and this infinity norm of y in this way. And which is more interesting, the C norm also has a similar property, but here we take the projective norm of the phi prime. So we can see that if this is equal to 0, then the injective norm of phi is just the injective norm of phi prime, and the C norm is just the projective norm of phi prime or phi bar. This is. And so note that here the dimension is one less than we had than the dimension for V. So from this we obtain compatibility conditions in centrally symmetric GPTs as follows. So we take a set of a tuple of elements, and we take this kind of representation. We put this 1/2 here to put it closer to the qubit effects. And we see that we have a very similar situation. So each Fy is an effect if and only if we have this inequality for the norms and alpha i's. And Fi is called unbiased if and only if this alpha I is equal to 1. And here the corresponding tensor has this form. So this element YF is obtained like this, and this is the tensor phi bar. And notice that for unbiased effects, this is always equal to 0. So we have this characterization. So compatible, so if you take effects F1 to Fg, if they are compatible, then the projective norm of this corresponding tensor is less or equal to 1. And in the case of unbiased effects, also the converse holds. So this, in particular, this extends the result for qubits to any number of effects and, in fact, any centrally symmetric GPTs. We also can use it for minimal compatibility degree in this way. So here directly we have equality with the projective injective ratio to the -1. Here we have to take with respect to the dual norm. Again, using the bounds, we obtain this lower bound. So this is tighter than we had in general, because this one less than the dimension of V. And this bound is actually attained, as I will show shortly. And the minimal compatibility degree for all G, if G goes to 1, that this gamma decreases to the 1 summing constant to the -1. Here we have to take the norm of yeah. So to show some examples, the first example is of qubit GPTs, where the norm is just the L infinity norm, and the state space is the hypercube. So here is an example where the state space is a square. This is a GPT known as the PR box, which is studied because it maximally violates the CSH inequality. And it turns out that this GPT attains the lower bound for compatibility degree. So it's exactly this maximum. Another example is of spherical GPTs, where the norm is the L2 norm and the state space is isomorphic to the Euclidean ball. Here, the compatibility degree is known exactly if the number of effects is less or equal to the dimension. But in the other case, we have these two inequalities. So this here in particular comes from the one summing constant. Okay, so for qubit effects, what can we say? So we have this equality for G equal 2 or 3. This was also previously known, but for a larger number of effects, we have this inequality. So we know that this is a sharp inequality by some random searches. And we know that for G coming to infinity, this decreases to 1/2, which is the one summing constant in this case. But the question whether this lower bound can be attained for some finite G is open, even for G equal to 4, we don't know. Okay, so what about more general quantum effects? Here this is no longer centrally symmetric, but we can show that it is connected to the matrix convex sets, which connects nicely to some previous results of Andreas and Ion. So first, let me tell you what is a matrix convex set. Matrix convex set is G variables, is a collection of G tuples of self-adjoint matrices for any dimension. And this collection is closed under direct sum. So if we take some collection at level k and some at level n, then the direct sum will be at level n plus k. And similarly, it's closed under application of unital completely positive maps between the levels. These matrix convex sets are studied in various contexts. They are related to optimization, because they describe the relaxations of some linear matrix inequalities, also in operator theory, dilations of operators, and they are also closely related to operator systems. The main examples of matrix convex sets are the matrix range. This is given by a tuple of self-adjoint operators on any Hilbert space. And the matrix range is just a collection of all images of this tuple under unital completely positive maps. Another example connected to the tuple of A's is the free spectrahedron. It's again a tuple of self-adjoint matrices satisfying inequality of this form. At level 1, this is a convex subset in RG. This is the usual spectrahedron. There is a natural duality of matrix convex sets, which is similar to the polarity of convex sets. So it is another matrix convex set such that this inequality is satisfied for all tuples in C. And in this sense, the free spectrahedron and matrix range are each other's dual. Okay, so there is also a notion of a maximal matrix convex set over a convex set. So if we have a convex set K, we can look at all matrix convex sets such that they are equal to K for n equal to 1. And there is a minimal and maximal such matrix convex sets, so over K. So there, all others are between these two. And there is a duality between this maximal and minimal set. Here we take the polar of K, and we see that the dual of the maximal set over K is C mean over K polar, and vice versa. If K is a polytope, then there are some tuples of operators such that C mean over K is a matrix range given by A, and C max over K is the free spectrahedron given by B. Okay, so we will see that these matrix convex sets relate to the C norm in the case of effects on of quantum effects. So if we take any tensor here in L infinity tensored with self-adjoint matrices, and we look at the injective norm, we see that we have this inequality if and only if this tuple is in the maximal matrix convex set over, this is the hypercube, the unit ball in L infinity. And the unit ball of the C norm is related to, similarly to the minimal matrix convex sets over the hypercube. To understand these minimal and maximal matrix convex sets, we have to look at the hypercube and also to its polar, the cross polytope, or this is the unit ball of L1 norm. Here, the matrix cube is a maximal matrix convex set over the hypercube. This is just tuples of self-adjoint contractions, and it is a free spectrahedron, and we use this notation here. And the matrix diamond, which is again a set of self-adjoint matrices satisfying these inequalities for all choices of plus or minus signs. And this will be the notation for this free spectrahedron. So here we can obtain a characterization of compatible quantum effects, which was previously observed by Andreas and Ion, but I think coming from a different direction. So this was this is the condition that C norm is less or equal to 1 is equivalent to this condition, and this minimal matrix convex set over hypercube is just a dual of the matrix diamond. This second condition is what was observed by Andreas and Ion, is in terms of the free spectrahedral inclusion, which says that the matrix diamond is included in the free spectrahedron given by this tuple of operators. Another characterization comes from the description of minimal matrix convex sets as a matrix range with respect to this set of commuting contractions AI. So the effects are compatible if and only if all the F tildes are obtained as images of these matrices under a unital completely positive map. And another condition comes from a different characterization of minimal matrix convex sets, which says that this tuple dilates to a G tuple of commuting contractions. Okay, so here we can obtain a minimal compatibility degree by using the results of the inclusion constant between the maximal and minimal matrix convex sets. And from this we obtain lower bounds for this value gamma. So 1 over square root of G. And here equality is attained for if the dimension is large enough, and is attained by in the case when these F tildes are anti-commuting self-adjoint unitaries. So we need a large enough dimension to have so many such unitaries. And Andreas and Ion also obtained a dimension-dependent bound of this form. Sorry. Thank you very much again. I apologize for the inconvenience I had with my technical problems. And thank you very much also for coming for the second half. And I am also grateful to John and the organizers for rescheduling my talk. Okay, so let me start. First, I would like to give a brief summary of what was said in the part one. So I was talking mainly about compatibility of effects in a GPT. And we have seen that this compatibility can be characterized by a cross norm, which we denoted by this C. From this, we obtained that the compatibility degree is lower bounded by this rho, which is the projective-injective ratio. And we also have a common lower bound for all G, which is the one summing constant. For centrally symmetric GPTs, we got some stronger results. In particular, we have an equality here, and this becomes a tight bound. For qubit effects, we get a tight lower bound of 1/2. And as it seems, this is the best bound on the compatibility degree for more than 3 effects. In the case of quantum effects, more general, not only qubits, we obtained that the unit ball of the C norm is related to the minimal matrix convex set over the hypercube, which leads us directly to the remarkable result of Andreas and Ion about the connections of compatibility to inclusion of the matrix diamond. So that was for the first part. In the second part, I would like to concentrate on the compatibility of measurements with any finite number of outcomes in a GPT setting. Here, the idea is actually the motivation, the first motivation for this joint work, and which was to connect two results. First was the results on compatibility of quantum measurements by inclusion of free spectrahedra, which can be generalized also in this setting from the setting of effects. And another characterization of compatibility in GPTs in terms of positive maps and entanglement breaking condition. So they both are equivalent to compatibility. So this clearly is an extension of this or generalization of this, but we wanted to see some direct way how to get from one condition to the other, because they are not obviously connected. And on the way, we also generalized the free spectrahedra to the setting of ordered vector spaces. So this will be the content of this part of the talk. Okay, so first I will shortly introduce the result for quantum measurements. Here, for effects, we had the matrix diamond and the inclusion constant and inclusion conditions for characterization of compatibility. And here the matrix diamond is replaced by a matrix jewel, which is a free spectrahedron in more variables here. It is given by this set of diagonal matrices, of these large diagonal matrices, and it is a maximal matrix convex set over this, which is essentially a convex direct sum of simplexes. The idea behind this is that the hypercube can be replaced by this product of simplexes, and this is here we replace the cross polytope by this polar. So now if we have quantum measurements, a G-tuple of quantum measurements or just collections of self-adjoint matrices, then we can state the conditions for compatibility in terms of spectrahedra inclusion or inclusion for the matrix dual. So we form this tuple of shifted effects for these measurements. And here we see that this inclusion at level 1, so this is the matrix dual, and then this is the free spectrahedron defined for these measurements. And this inclusion at level 1 is just equivalent to the fact that these really are measurements or effects summing up to 1. And the inclusion of all spectrahedron or the full spectrahedra is just equivalent to compatibility of these measurements. And we also know from characterization of these matrix convex sets and their duality that this condition is equivalent to the fact that this tuple F tilde is in the matrix range of these defining matrices. So this was for the situation in quantum measurements. Now we look at the condition for general measurements in GPTs. So for this, I will need a little bit of more preparations, but these are just well-known things, so I will go through that quickly. So we have a two-ordered vector space, and we can form the tensor product. So, but in the tensor product of vector spaces, we have to choose a positive cone. And basically the condition is that this tensor cone is between the minimal and the maximal tensor cones, where the minimal tensor product just contains of all separable elements, which are sums of a simple tensor of positive elements. And the maximal tensor product is obtained by duality from the minimal tensor product. And this inclusion just says that we require that all separable effects are positive. Now, if we have a map between ordered vector spaces, which is positive, which means that it preserves the positive cones, and we have another arbitrary ordered vector space, then it is easy to see that this positive map is completely positive with respect to both maximal and the minimal cone, which means that it maps preserves the maximal cones and the minimal cones. And we say that this map is entanglement breaking if for any L, the phi tensor identity maps any positive tensor to a separable one. So this is a direct generalization of entanglement breaking quantum channels. So to come back to measurements, let us have a GPT given by this triple and a G-tuple of measurements with this set of outcomes. And their easy observation is that this tuple of measurements defines an affine map from the state space of the GPT to this PK, which is a product of simplexes. This is seen very simply because any of these measurements is just an affine map into one of the simplexes. So the tuple is mapped to the product. And compatibility can be written as this diagram here. So this is these are our measurements. This is the joint measurement, and this J corresponds to taking the marginals. So we can easily see from this that if we extend all these maps to positive maps, so these are just bases of some cones, and we can represent this as a base of a positive cone, and then we have unique extensions to positive maps, and the compatibility condition is that these measurements are compatible if and only if this F is entanglement breaking. So how does this connect to the condition which we have seen for quantum measurements? So to see this, we need a special representation of pk as a state space in a GPT. So for this, we take the matrices AK, which are diagonal. So we can represent them as by these diagonal vectors. And we take a span of these vectors and the identity, which then becomes a subspace of this RK. And this actually forms a basis of this space, so they are linearly independent. If we take an orthogonal projection onto this subspace, then we obtain that if we take this subspace K with the projection of the simplicial cone and the vector of all units, then this is a GPT whose state space is just the projection of this simplex and is isomorphic to PK. And what is important here that this restriction to the simplex corresponds to taking marginals. And we also need a dual space, which is just, we can take it just to be EK, but with different cone. Here the cone is the intersection with the simplicial cone. So with this definition, the affine map given by measurements extends to a positive map between the corresponding spaces. And we also need here this adjoint map, which will be important for us. And this adjoint map, of course, is determined by its values on the basic elements. So here we see that it has to be unital, and from its values on the basic vectors, we easily obtain all the measurement effects. And as any positive map, these maps correspond to a tensor in this maximal tensor product of the cones. So here is tensor is given here again, the measurement effects appear. So now, in terms of the extended positive maps, the compatibility is written like this diagram, but if we apply the duality, we obtain here a similar diagram for the adjoints. And if we know that J is just a projection, then here we obtain an inclusion, which means this means precisely that the adjoint map has a positive extension to all this space with the simplicial cones. So from this, we obtain the following equivalent conditions for compatibility. So first we have this kind of factorization through the simplicial cone, which is equivalent to F being entanglement breaking. Equivalently, also the adjoint is entanglement breaking. And another condition which we have seen here is that the adjoint extends to a positive map from the simplicial cone here to the dual to the space of effects. And we also have a condition for this corresponding vector, which this cone here is the minimal tensor cone in between these two cones. And this is just the projection of the unique tensor cone between A plus and the simplicial cone. So let us look now at the quantum case. So now these Fs are quantum measurements, and we can see that that EK with this if we take this dual cone here, then this is actually isomorphic to the operator system generated by the diagonal matrices here. And our adjoint map is a unital and positive map from this operator system to the space of matrices, or to the matrix algebra. And since the operator system is commutative, then this adjoint map has a positive extension, if and only if it's completely positive, which means that this F star has a unital completely positive extension to a map between matrix algebras, which in other words means that these vectors here, F tildes, are in the matrix range given by the matrices AK, which brings us directly to this spectrahedral inclusion conditions. So this is one way how these two conditions connect. But we also can try to generalize the notion of free spectrahedron directly to the setting of ordered vector spaces. So here we can introduce generalized spectrahedron. So we have again two ordered vector spaces, and we have a fixed tensor cone in the tensor product, and we have some elements A1 to AN in this space. And we define a generalized spectrahedron, so like this. So if you remember the definition of a free spectrahedron, this has some similarities, but there are also some important differences. So first of all, this is not bounded, so it is always a cone. It is because in the case of matrices we always had some inequality, so this is less or equal to the identity matrix. But in general, we do not have any distinguished identity in tensor in ordered vector spaces, so we have to assume that it just belongs to some cone. And this cone also has to be fixed. So in case of matrices, we have a distinguished cone, positive definite matrices, but in general, that is not the case. But fortunately, the generalized spectrahedron has some good properties. So if we assume that these A's here are form a basis of the vector space, then if we take this L to be just the space of reals with a positive cone, then this generalized spectrahedron is just isomorphic to the fixed cone C. And more importantly, if we take any other ordered vector space, any other tensor cone C prime, and any map from E to F, then the positivity of the map phi tensor L, phi tensor identity with respect to these two cones is positive if and only if we have this inclusion of generalized spectrahedra for A and for phi A. So we will use this condition to characterize compatibility. So for this, we introduce a GPT dual, which is a special generalized spectrahedron. So we have this fixed subspace as before, and these basis elements. And we define the GPT dual for any ordered vector space as the generalized spectrahedron with respect to this basis and the maximal cone. So this is fixed for any GPT, but it is given by the numbers of outcomes of the measurements. So now we can, similarly as for the quantum measurements, we can characterize compatibility in terms of inclusions of generalized spectrahedra. So if we now we have to take this tuple of F tildes, but we also have to add this unit effect. That's because we have this unbounded spectrahedron. So here, if we take Fi initially just to be a collections of elements in A, so some functionals, but that these collections are actually measurements if and only if we have this inclusion at the level at the one-dimensional level. And here this spectrahedron is given by this set of operators of elements. And these measurements are compatible if and only if we have this inclusion, but at the level of V. So this space V is characterized as the GPT, but here we have to take the minimal cone. This in case that we are working with effects, so all measurements have only two outcomes. We obtain the GPT diamond, which has this easy sort of definition. And if L is equal to V, then we can see that the GPT diamond that is directly connected to the dual cross norm, to the this C norm, which we introduced for compatibility. So this is yeah, naturally connects to the previous results. We also have some relation to the matrix dual. So in case of quantum theory, where this ordered vector space is given by self-adjoint matrices with the positive cone, the generalized GPT dual is connected to the matrix dual like this. So here we have some additional positive definite matrix, and here we have the elements of the matrix dual sandwiched between the square root of Z0. And at dimension 1, this means that the GPT dual is just isomorphic to the cone, which is generated by this essentially the direct sum of simplexes. We can, using the GPT dual, we can also characterize the compatibility degree for these sets of measurements very similarly as it was done for the matrix diamond and spectrahedral inclusion. So we can see that this compatibility degree, or the minimal compatibility degree, is just the supremum of all S, such that this GPT dual multiplied by S is contained in all these generalized spectrahedron for all kind of sets of measurements. Here, from this, we can obtain some bounds on this compatibility degree. So if we look at the GPT dual and the GPT diamond at level 1, they have these connections, and from this we obtain a lower bound for the compatibility degree in terms of compatibility degree for effects. And this upper bound is just obtained from the condition that or from the observation that if we increase the number of outcomes, we can only get measurements which are less compatible in a sense. Okay, sorry. We can also define from these connections some sort of incompatibility witnesses. So what is an incompatibility witness? It's a sort of way how to detect that some measurements are not compatible. A general definition of an incompatibility witness could be given as a functional, or more generally a map on G tuples of measurements, such that all compatible tuples are containing some given set S. And such witness is said to be strict if some tuple is not mapped into this set. So it's not compatible. So in this case, the witness detects non-incompatibility of this tuple. So from these various characterization of compatibility, we get several definitions of incompatibility witnesses. So for effects, we can take all tensors here in this tensor product, such that the dual norm, the dual C norm is less or equal to 1, but the projective norm is larger than 1. So this means that this is a functional such that the tensors related to any compatible set of effects, it has a value less than 1, but there is some incompatible tuple of effects such that the functional gives the value larger than 1. So it's a strict incompatibility witness. So another definition is just take any element in the GPT dual. For compatible sets of measurements, this always maps in this way into this minimal cone. And again, if some tuple of measurements is seen to be mapped outside of the cone, it has to be incompatible. Another way to view an incompatibility witness is as a positive map between these spaces, such that the trace of this composition, it's just the trace of linear map, is negative for some f. Or we can also view the witnesses as images of this pk, so this product of simplexes in the positive cone V plus. This is a strict incompatibility witness if this image is large in some sense. So to conclude, so what is maybe worth remembering from this talk is that we have found there are some connections of compatibility or incompatibility of measurements in GPT to various different problems. So first is tensor norms in Banach spaces and the ratios, problems of inclusion of free spectrahedra, then properties of positive maps in ordered vector spaces, and also inclusions of generalized spectrahedra. So this may give, so these connections I think are interesting and may be fruitful, maybe in both directions. So we can learn something about incompatibility from results in these theories, but maybe also the other way around. So this is all. Thank you very much.
Thanks very much, Anna.